Good day, learners. Welcome to our physical sciences lesson. My name is Amenim Kize. This lesson is brought to you by Sci-Bono Discovery Center in collaboration with Gauteng Department of Education. Right, grade 11 learners. Today we are going to focus on knowledge area chemical change. And then the topic under chemical change is quantitative aspects of chemical change. Then according to our exam guide, this is what we need to focus on. And we did touch on atomic mass and mole concept, last week, describing the mole as the SI unit for the amount of a substance, define 1 mole of a substance, define the relative atomic mass, describe the Avogadro's number, define the molar mass, describe the relationship between molar mass, relative molecular mass, and relative formula mass, molecular formula and the formula masses, calculating mass, molar mass, and number of moles using the equation N equals to mass over molar mass. Right, so today our focus is more on determining what are the empirical formula and the molecular formula of a substance, and also, calculating what the percentage composition or the percentage of what of an element to a certain compound. Then next week we'll be focusing on what calculating the number of moles of water of crystallization, percentage composition, also the definition of percentage composition, defining the concentration of a substance of a solution, and also calculating what the concentration of a solution. And then we did look at what the Avogadro's law and calculating what the volume of gases at STP. We did look at that last week, and then next week we'll be focusing more also on what the basic stoichiometric watt calculation. But learners, our focus today is on empirical formula and the percentage watt composition. It's what we are going to focus on today. So it's part of quantitative aspects of chemical change. So this is what we are going to focus on next week. This is our examination examination guideline. So it's what we need to focus on, or it's what we need to do under what the quantitative aspects of chemical change. Right. So let's start with the percentage composition, learners. So the percentage composition, I think all of us by now we know that a percentage is equals to 100%. And when it comes to chemistry, this is how we define percentage composition. Percentage composition is defined as the mass of each atom present in a compound expressed as a percentage of total mass of the compound. So the focus here, it's not more on the definition, but the focus is more on the calculation of the percentage of the percentage composition. So it's what we need to know, according to our exam guide. Right, so these are the steps that you need to follow when you want to calculate the percentage watt composition, right? First thing that you need to do, which is what we did last week. All of us by now, we know how to calculate the molar mass. We did that even in grade 10, all right? So we know how to calculate the molar mass of a compound. So if you want to calculate the percentage composition of an element in a certain compound, first thing that you need to do is to calculate the molar mass of the whole compound, right? So remember, to calculate the molar mass, you need your periodic table, okay? So you will get the relative atomic masses from the periodic table. And then that will assist you to calculate what the molar mass of the whole compound, right? Then determine the contribution to the total mass or molar mass of the compound of each element present in the compound, and express it as a percentage of molar mass of the compound. So first thing that you need to do is to calculate the molar mass of a compound. And then after calculating the molar mass of a compound, you express the contribution of each element present in the compound in a form of a percentage, right? For example, let's look at this example. Determine the percentage composition of methane, right? So when it comes to methane, right? So in other words, what is important here, learners, is to make sure that you know how to move from the chemical formula, sorry, from the chemical name to the chemical formula, right? For example, here we are given what? Methane, right? So what is the chemical formula of methane? Is CH4. So the atoms that are present there, or the elements that are present there, is carbon and what? And hydrogen, okay? So first thing that you need to do here is to calculate the molar mass of the whole compound, which is your CH4. So the molar mass of CH4, it's M. So the molar mass of CH4, which is methane, C, that is the carbon, and then what is the mass or the relative atomic mass of carbon from the periodic table is 12, right? Plus you have 4 hydrogen atoms, right? Then what is the relative atomic mass of hydrogen? It's 1, so it will be 4 times what? Times 1. So what is 12 plus 4? It's what? Is 16 what? Grams per what? Per mole. So that is the first thing that you need to do. Calculate the molar mass of the whole compound. So we know how to do that in grade 10. Even last week we were focusing on that, right? So you're having 16 grams per watt per mole here. Then let's calculate the percentage of each element in that compound. So we are having 2 elements there, is the carbon and what? And the hydrogen, all right? So let's calculate the percentage of carbon in methane and also the percentage of hydrogen in what? In methane. So how do we calculate the percentage composition? So the percentage composition, it's always percentage composition equals to molar mass of an element, right? So it's the molar mass of an element, right? You divide that by the molar mass of a compound, right? Then you multiply by what? By 100. So you're expressing that in what? Actually as a percentage, right? So molar mass of an element divided by what? The molar mass of what? Of a compound. So what is the molar mass, for example, for carbon in methane? The molar mass of carbon is 12, right? And then what is the molar mass of what? Of methane. The molar mass of methane is what? Is 16. So you have 12 divided by 16 times 100. So the percentage of carbon in methane is 75 what? 75%, right? Then what about the percentage of hydrogen in methane? One, what you need to check, you need to check how many atoms of hydrogen are present in one molecule of methane. So the number of atoms of hydrogen that are present in one molecule of what? Of methane is 4. So here is 4, multiply that by 1. Where is that 1 coming from? Remember, to calculate the percentage composition, we say a molar mass of an element divided by the molar mass of what? Of a compound. But let's not forget the number of atoms of that element present in that compound, all right? For example, in this case, for hydrogen, we have 4 hydrogen atoms in one molecule of what? Of methane. Then from there, what is the relative atomic mass of hydrogen? From the periodic table, it's what? It's 1. So hence we said 4 times 1 there divided by 16, which is 4 over 16 multiplied by what? By 100. So the percentage of hydrogen in one molecule of methane is what? Is 25%. So it's simple, learners, to calculate what? The percentage composition of what? Of a certain element in what? In a certain what? Compound, right? So first thing that you need to do, you calculate the molar mass of the whole compound, right? Then from there, how to calculate the percentage composition? Percentage composition is given by what? Molar mass of an element, divide that by what? Molar mass of a compound, multiply by what? Multiply by 100. So let's look at other examples, but it's simple. Calculate the molar mass, then from there of the whole compound. Then percentage composition is given by what? The molar mass of an element, divide that by what? By the molar mass of what? Of a compound, right? So determine the percentage composition of the following. So you are given a copper sulfate there. So first thing that you need to do is to calculate the molar mass of copper sulfate, right? So copper sulfate, the relative atomic mass of copper from the periodic table is 63.5. All right, then for sulfur is 32, and then for oxygen is 16, but it's 16 times 4. Why are we multiplying by 4? Because there are 4 oxygen atoms that are present in 1 molecule of copper of copper sulfate. Then what is the molar mass of copper sulfate is 159.5 grams per mole. 159.5 grams per mole. Then from there we can calculate the percentage of each element in that compound, right? So what is the percentage of copper? Percentage of copper, it will be what? The molar mass of copper divided by the molar mass of copper sulfate, right? So it's the molar mass of copper. And how many copper atoms are we having there? It's only one. Hence, we are having 63.5. Actually, it's that 63.5 times 1 because you have one atom of what? Of copper in 1 molecule of copper sulfate, right? Then you divide that by what? By the molar mass of the whole compound, which is 159.5. So it's 63.5 divided by 159.5, multiply that by 100. Then what is the percentage of copper in copper sulfate? Is 39.81%. Then what is the percentage of sulfur? So there are 3 elements there. It's copper, sulfur, and oxygen, right? So now let's calculate the percentage of sulfur in 1 molecule of copper sulfate. So it will be molar mass of what? Of copper. Sorry, not copper, but the molar mass of sulfur divided by the molar mass of copper sulfate. So it's 32, which is the molar mass or relative atomic mass of what? Of sulfur. Divide that by what? By 159.5 times 100. Then the percentage of sulfur in copper sulfate is 20.06%. It's 20.06%. Then what is the molar mass of the percentage of oxygen in 1 molecule of copper sulfate? It will be 16 times 4. Why 16 times 4, learners? In 1 molecule of copper sulfate, we have 4 oxygen atoms. So it's 4 multiplied by the relative atomic mass of oxygen, which is 16 from the periodic table. So it's 16 times 4, 4 times 16, divided by the molar mass of copper sulfate, which is 159.5. Multiply that by what? By 100. Then the percentage of oxygen in 1 molecule of copper sulfate is 40.31. So when you add this 39, this 20, and then this 40, you must get what? 100%. So this is how we calculate the percentage composition of elements in a compound, all right? Then this is another example. We are given potassium permanganate, right? So we are given potassium permanganate. So in potassium permanganate, there are 3 elements there. It's potassium, it's manganese, and oxygen, right? So how many potassium atoms are present there? Is only 1. And how many manganese atoms are present? Is only 1. And how many oxygen atoms are present? It's what? It's 4, all right? So again, first thing that we need to do so that we can be able to get the percentage of potassium, the percentage of manganese, and the percentage of oxygen in 1 molecule of potassium permanganate, right? So we have to start by calculating what? The molar mass of what? Of potassium permanganate. So potassium is 39, that is the molar mass or the relative atomic mass from the periodic table. And then manganese is 55. And then oxygen is 16. So it's 16 times 4 because there are 4 oxygen atoms there. So 39 plus 55 plus 16 times 4 is 158 grams per what? Grams per mole. That is the molar mass of potassium permanganate, all right? Then now we can calculate the percentage of each element in that compound. So this is the percentage of potassium, right? Which is 39 over 158 times 100. Then the percentage of potassium is 24.68%. And then the percentage of manganese, the relative atomic mass or the molar mass of it is 55 divided by 158. So what is 55 divided by 158 times 100 is 34.81, right? So that is the percentage composition of what manganese atom there or element in potassium permanganate, right? Then for oxygen it's 16 times 4, then divide by 58 times 100, and it's 40.51%. So these actually this is how we can calculate the percentage of each element in what? In a compound. Start with the molar mass of the whole compound. Then how do we calculate percentage composition? The percentage composition is given by what? Molar mass of an element divided by molar mass of what? Of a compound. Multiply that by what? By 100. But again, please be careful when you're using that. Make sure that you consider what? The total number of atoms present for that element in that compound. For example, in this case, how many potassium atoms? 1. How many manganese atoms? 1. How many oxygen atoms? 4. Hence here we multiplied that 16 by what? By 4. Then you'll get the correct percentage composition for that for that element in that compound. Right. Then this is an activity where you learners are expected, to do it. Right. First question, they want you to define the term percentage composition. The second question, they want you to, to find the value of X there. If the compound potassium sulfate K2SO4 oxygen makes up, in the compound potassium sulfate, right, which is K2SO4, oxygen makes up X percentage of the mass of the compound, right? So determine the value of X, all right? So what is the value of X? Is it 36.8? Is it 9.2? That is option B. Is it C, which is 4? Is it D, which is 18.3? So, but you cannot just, learners, you cannot just choose any option here, all right? First thing that you need to do is to calculate and get the correct answer. And then after doing that, then you'll be able to choose what? The correct what? Option. All right. So first thing that they want you to do here is to define the term percentage composition. And then the second question, they want you to calculate what? The percentage of what? Of oxygen in potassium what? Sulfate. All right. Then your number 3, they want, okay, this is number 3. Fertilizers contain nitrogen needed by plants to grow. Then ammonium nitrate is used as a fertilizer. And what is its chemical formula is NH4NO3. Calculate the percentage of nitrogen, mass of nitrogen in 12 grams or kilograms bag of fertilizer. Calculate the percentage of chlorine. So let's start with the first question. So they want us to define percentage composition. That is our number 1. So percentage composition. Percentage composition. So where are you going to get this definition, right? You'll get this definition from what? From the exam from the exam guideline, right? So let's go back to our exam guideline. So according to our exam guideline, this is how we have to define percentage composition, right? So what is percentage composition? Is the mass of each atom. It is the mass of each atom present in a compound expressed as what? As a percentage, right? Then that is how we have to define what the percentage composition. It is the mass of each atom present in a compound expressed as a percentage of the total mass of the compound, right? The mass of each atom present in a compound which is expressed as what? As a percentage of the total mass of what? Of the compound, right? Then that is how we have to define what? The percentage composition. Let's go to the next question, right? The next question, what are they looking for? They are looking for what? The value of X, right? So for the value of X, you have potassium here? Sulfate, right? So you have potassium sulfate K2SO4. So first thing that we need to do here, learners, is to calculate the molar mass of potassium sulfate, right? So the molar mass of potassium sulfate, M for potassium sulfate, all right? So potassium, how many atoms of potassium are present in one molecule of potassium sulfate? There are 2. So it will be 2, multiply that by what? By 39, okay? Which is the relative atomic mass from what? From the periodic table, okay? Then plus sulfur, sulfur is only one atom there, so it's plus what here, 32. Then plus 16 times what? Times 4. Why 16 times 4? There are 4 oxygen atoms, all right? Then the relative atomic mass of oxygen from the periodic table is what? It's 16. So what is your answer here, right? So let's use our calculator. Okay. So you have 2 multiplied by 39, right? What are we having there? It's 78. So it's 78 plus 32, right? Plus 16 times 4, okay? So which is 174, okay? So it's 174. That is our relative or that is our molar mass of potassium sulfate, 174. So let's go back. So it's 174 grams per mole, okay? That is the molar mass of potassium sulfate, all right? Then what are they looking for? The value of X, right? So what is X? They are asking you to calculate the percentage composition of what? Of oxygen, right? So percentage oxygen, right? It will be molar mass of oxygen, right? Divide by molar mass of potassium sulfate, okay? Right, what is the molar mass of oxygen? It's 16. But how many oxygen atoms are we having there? They are 4. So it's 16 times 4 divided by 174. Multiply that by what? By 100. Then we'll get our answer as a percentage, right? So it's 16 times 4. So let's calculate. So it's 16. So 16 times 4. What are we having there? It's 64. So we are having 64 divide by 174, okay? Multiply that by 100, okay? So what are we having here? It's 36.78. 36.78. 36.78%. Right? That is the percentage of what? Of oxygen. Then let's go back to the question because it's a multiple choice question. But for us to get the correct answer, we have to start with these calculations. All right? So let's go back and see. Yeah. So this is the correct what answer. So they round off the answer to 1 decimal place. Okay? So the correct answer here will be what? Will be A. Okay? So I hope we are still together. They wanted us to calculate what? The percentage what? Composition. So let's look at number 3. So number 3, what are they looking for? Right? They are looking for the percentage of nitrogen in ammonium nitrate. The percentage of nitrogen in ammonium what? Nitrate. So ammonium nitrate, where are we going to start? Ammonium nitrate is NH4NO3. All right? So we have to start by calculating what? We have to start by calculating the molar mass of ammonium nitrate, right? So the molar mass of ammonium nitrate, right? So check here the number of nitrogen atoms here. It's 1. The number of nitrogen atoms, it's 1, 2, right? So it's 2 times what? 14. 14, that is the relative atomic mass of what? Of nitrogen from what? From the periodic table. How many hydrogen atoms? There are 4, so it's 4 times 1. Okay, plus how many oxygen atoms? There are 3. So it's 3 times what? Times 16. Okay, 3 times 16. So where is that 2 coming from? So there are 2 nitrogen atoms, it's 1, 2. So it's 2 times 14. And then how many oxygen, so hydrogen atoms, there are 4, so it's 4 times 1. How many oxygen atoms? There are 3, so it's 3 times 16. So what are we having here is 28 plus 4 plus 3 times 16. Let's check. Okay. So we are having what? 28 plus 4 plus 3 times 16. Okay, so it's 80, right? That is the relative or the molar mass of what, of ammonium what, nitrate is 80. So it's 28 plus 4 plus 3 times 16, so it's 80. Okay, so here we are having what, 80 grams per mole. So we're having 80 grams per what, per mole. So they're looking for what? Let's check. They're looking for the percentage of nitrogen in ammonium what, nitrate. Percentage of nitrogen in ammonium what, nitrate. So percentage nitrogen, it will be molar mass of nitrogen, right, divide by molar mass of ammonium nitrate. Okay, ammonium nitrate multiplied by 100. All right, so molar mass of nitrogen is 14, but how many nitrogen atoms are present in one molecule of ammonium nitrate? It's 2. So it's 2 multiplied by 14 divided by the molar mass of ammonium nitrate, which is 80, then multiply that by 100, right? So you're having 28 over 80 times what, times 100. Then you will get what, the percentage composition or the percentage of nitrogen in one molecule of ammonium what, nitrate. Okay, so let's calculate that. So it's 28 divided by 80, né? So it's 28 divided by 80. Okay, multiply that by 100, right? Then it's 35 what, percent. So it's 35%. So it's 35 what, percent. So the percentage of nitrogen in ammonium nitrate is 35 what, percent. Then 3.2 mass of nitrogen in 12 kilograms a bag of fertilizer, right? So what are we having now? We are having a bag, right? This is a bag of fertilizer, right? And then what is the mass of this bag? Is 12 grams or kilograms, sorry. So we have 12 kilograms there. Remember, it contains what? Ammonium what? Nitrate. So what are they looking for? The actual mass now, right? So they're looking for what? The actual mass, right? Remember, in these 12 kilograms, you have nitrogen, you have hydrogen, you also have what, oxygen and other substances, all right? So they're looking for what here? The actual mass of what, of nitrogen in that bag of what, of fertilizer, all right? So how are we going to get the actual mass? The actual mass, remember, we got the percentage of what, of nitrogen in that bag of fertilizer, and the percentage is 35. Then what are we supposed to do for 3.2 is to calculate the 35% of 12 grams, all right? 35% of what? Of 12 grams. So what is 35% of 12 grams? So it's 35%. So it's 35% of 12 kilograms. Okay? So 35% of 12 kilograms is the same as 35 divided by 100 multiplied by what? 12. Okay? Then we'll get the actual mass of nitrogen in 12 grams of what? Of that fertilizer, right? So it's 35% of 12 kilograms. Then 35 divided by 100 multiplied by what? Multiplied by 12. So 35 divided by 100 is 0.35. So it's 0.35 times what? Times 12. Okay? 0.35 times 12. 0.35 multiplied by 12. All right? So I'm having 4.2, right? So 4.2 kilograms. 4.2 kilograms. So it's 4.2 what? Kilograms. So the actual mass, so this is your 3.2. This is your 3.2, and then this is your what? Your 3.1. Okay. So your 3.2, they are looking for the actual mass of nitrogen in that 12 kilograms of fertilizer, right? So we got the percentage of nitrogen in ammonium nitrate as 35%. Then now we're required to find what the 35% of what of 12 kilograms. So we got 4.2. All right. Then let's look at number 4. Number 4, they're looking for what? The percentage composition also, but the focus here is just chlorine, the percentage of chlorine in each of the following compounds. You have copper 2 chloride, okay? You have copper 2 chloride. That is the chemical name here, copper 2 chloride. That is copper 2 chloride. And then this one is ammonium chloride. Ammonium chloride. Okay, so they are looking for the percentage of chlorine in copper 2 chloride and the percentage of chlorine in ammonium chloride. Right, for us to get the percentage of chlorine in copper 2 chloride and the percentage of chlorine in ammonium chloride, we have to start by calculating what? The molar mass of each compound there. All right. So molar mass of each compound. Let's start with 4.1. Okay. Let's start with 4.1. 4.1 is copper 2 chloride. Let's calculate the molar mass of it. Let's calculate the molar mass of it. That is our 4.1 is copper 2 chloride. So the molar mass of copper 2 chloride will be 63.5 plus what? 2 times 35.5. These values, they are from the periodic table, learners, right? So 63.5, that is the relative atomic mass of copper. 35.5, that is the relative atomic mass of what? Of chlorine. But why I've multiplied by 2 there is because there are 2 chlorine atoms in that molecule. Or there are 2 chlorine atoms in that compound, right? So it's 63.5 plus 2 times 35.5. So it's 63.5 plus 2 times 35.5, right? Okay. So what are we having here? We're having 134.5, 134.5 grams per mole, right? Then from here, we can calculate the percentage of what? Of chlorine, right? So percentage of chlorine, so molar mass of chlorine, there are 2 chlorine atoms, so it's 2 times 35.5, all right? Divide that by what? The molar mass of the whole compound, which is 134.5, then multiply by what? By 100, right? So let's check the answer here. So you have 2 times 35.5, right? Which is 71 divided by what? 134.5, okay? Which is what? Multiplied by 100, right? So the percentage is 52.79. 52.79. 52.79%. That is the percentage of chlorine in what? Copper 2 chloride, all right? So what will be the percentage of chlorine in ammonium chloride? Percentage of chlorine in ammonium chloride, percentage of chlorine in ammonium chloride. Right, percentage of chlorine in ammonium chloride, start with the molar mass of ammonium chloride. Okay. Ammonium chloride, nitrogen atoms is 1, so it's 14 plus 4 times 1, right? Plus what? Chlorine, which is what? 35.5. So 14 plus 4 plus 35.5, 14 plus 4 plus 35.5. So what are we having there? It's 53.5. So that is the molar mass of ammonium what? Chloride. 53.5. 53.5. So we have 53.5 grams per mole, right? Then now let's calculate the percentage of chlorine. It will be molar mass of chlorine, which is 35.5, divided by the molar mass of ammonium chloride, which is 53.5. Multiply that by 100. Then let's check the percentage of chlorine in ammonium chloride. Chlorine in ammonium chloride. Right, so here we are having 35.5 divided by answer, which is 53.5. Okay, equals to, you multiply that by what? By 100. Okay, so what are we having here? We are having 66.36, 66.36, ne? So 66.36 what percent. So yeah, this is how we can deal with calculations on percentage composition. All right. So now let's focus on the empirical formula and the molecular formula. Right. So empirical formula and the molecular formula. What is the empirical formula? So the empirical formula, it shows what the simplest whole number ratio of atoms present in in a compound, right? So that is the formula that shows the simplest whole number ratio of atoms present in in a molecule or in a compound, right? So according to your exam guide, this is how we have to define the empirical formula, which is the simplest whole number ratio of atoms in in a compound. All right. So the difference between the empirical formula and the molecular formula, the empirical, it shows the simplest ratio. Maybe let me just give you an example. Right. You have C5H12, right? C5H12 is pentane. That is the chemical name, right? Sorry, pentane, sorry about that, pentane, right? This is the molecular formula of pentane. Right? This is the molecular formula of of pentane. So molecular formula is the actual formula, right, of a compound, right? It shows the exact number of atoms, right? And the number of atoms present in a compound. It shows the exact number of atoms present in that compound, right? That is the molecular formula. So it's the actual formula. Then the empirical, we are saying it shows the simplest whole number ratio of atoms present in in that compound. It shows the simplest whole number ratio of number ratio of atoms present in that compound. So for example here, so this is for C5H12, yeah, this example it's not going to work for me. So let's use C5. Let's use C6. Sorry, not here. It was C5. Let's use C6H14. So C6H14, that is hexane, right? Okay. So C6H14. So the highest common factor between 6 and 14 is is 2. So you can divide this by 2, divide this by by 2. So I'm having C3H7. So what is this C3H7? Is the empirical formula of hexane, right? Empirical. This one will be the empirical formula. All right. So that is the difference between the molecular formula and and the empirical formula. So the empirical formula shows the simplest whole number ratio of atoms present in in a molecule or in a compound. But what about the molecular formula? It shows the actual number of atoms present in a compound, right? So that is the difference between your molecular formula and the empirical formula. So for example, I've used hexane there. Hexane, the actual formula, which is the molecular formula, which shows the actual number of atoms are present in that compound, it's C6H14, right? Then the one that shows the simplest whole number ratio, it's what is the empirical, and I've divided 6 by 2, 14 by what? By 2, because the highest common factor between 6 and 14 is what? Is 2. Hence, I divided by what? By 2. So C6H14, that is the molecular formula of hexane. Then C3H7, that is what? The empirical formula, because it shows the simplest ratio, or the simplest whole number ratio of atoms present in what? In a compound, right? Then, how do we determine the empirical what formula? How do we move from empirical formula to molecular formula, right? So this one is simple, right? If we are given the molecular formula, you can just move from the molecular formula to what? To empirical. For example, I gave you what? Hexane, right? Which is C6H what? H14, right? Then that C6H14, that is the molecular formula. So it's easy for me to move from molecular formula to what? To empirical, because for me to move from molecular to empirical, I have to find the highest common factor, right? For example, in this case, between 6 and 14, which is what? Which is 2. Then divide each value there by what? By 2. 6 divided by 2 we got 3. 14 divided by 2 we got what? 7. So that C3H7 is the empirical what? Formula, right? But how do we determine the empirical formula given the percentage composition, right? How do we determine the empirical formula given the percentage what? Composition of each element present in that compound? All right, so this one is easy, straightforward. Given the molecular formula, we can move from molecular to empirical. But now, sometimes in most cases, actually, you will be given what the percentage composition, right, or the percentages, and you have to move from percentages to what? To a chemical formula, or to an empirical formula. From empirical formula to what? To molecular formula, right? Then these are the steps that we need to follow when we want to determine what the empirical formula of what of a substance. First thing that we need to do, okay, they will give you what the percentage, right, of each element in that compound, right? So what do? You express the percentages as masses, right? That is the first thing that you need to do. Express those percentages as what? As masses. From there, convert the mass to what? To number of moles, right? You convert those masses. So first thing, you'll be given the percentages. So from percentages, you convert those percentages to what? To masses, right? Then from there, calculate the number of what? Of moles. And then after calculating the number of moles, determine the ratio of the different elements in the compound by dividing the number of moles of each element by the smallest number of what? Of mole. So first thing, it should be what? Express those percentages as masses. From there, convert those masses to what? To number of moles. And then 3, find the ratio of what? Of those elements, right? How do you find the ratio of those elements, right? You have to divide the number of moles of each element by the smallest number of what? Of moles, right? Then from there, express the ratios as the smallest whole number, and then these values are the subscript of atoms in the empirical what? Formula. That is how we have to, these actually are the steps that we need to follow when we want to determine the empirical formula of what? Of a compound, right? Then from empirical to molecular formula, we'll come to that, né? But it's easy, right? After getting the empirical, find the molar mass of the empirical, because you'll be given the molar mass of what? Of the molecular formula, right? So they will give you the molar mass of the molecular formula, then you get the empirical formula. Then after getting the empirical formula, you calculate the molar mass of that empirical formula. Then to get the actual formula or the molecular formula, you will divide the molar mass of the molecular formula divided by what? The molar mass of what? Of the empirical formula. Then you will be able to get the molecular what? Formula of that element, or sort of that compound, right? So first thing, if you're given percentages, you express those percentages as masses. Number 2, you convert those masses to number of moles. 3, find the ratio of those elements. How do you find the ratio? You divide the number of moles of each element by the smallest number of moles. Then from there, you'll have your what? Your empirical. How do you move from empirical to molecular? then they will give you the mass of the molecular, right? Then you will divide that mass of the molecular formula, right, by the molar mass of the empirical. Then from there you'll be able to get the molecular formula of what? Of a compound, right? So this is an example, right? So mercury forms a compound with chlorine that contains 73.9% mercury and 26.1% chlorine per mass. Calculate the empirical formula of the compound, or determine the empirical formula of what? Of the compound, right? So first thing that we need to do, we are given the percentages, right? So what is the percentage of mercury? It's 73.9. What is the percentage of chlorine, right? Is 26.1. So we want to find the empirical formula of this compound, right? So mercury is 73.9, and then chlorine is 26.1. So first thing that you need to do is to express the percentages as what? As masses, right? So you assume that the sample is 100 grams, so which means that the mass of mercury, right? So assume that it is 100 grams sample of the solid. Therefore, it contains 73.9 grams mercury, right? That is 73.9 grams of mercury, okay? Then the percentage of chlorine is 26.1. Then it means that we have what? 26.1 grams of what? Of chlorine. Now we have the masses. So you express those percentages as what? As masses. So if you're having 73.9%, it is the same as 73.9 grams. If you're having 26.1%, it is the same as what? 26.1 grams. So you are having the mass now. Then from here, you have to calculate the number of moles of each element, all right? So how do we calculate the number of moles of each element? If we are given the mass, how do we calculate the number of moles? The equation that we use, number of moles is mass over what? Molar mass, right? So what is the mass of mercury? The symbol for mercury, or the chemical symbol for mercury, is Hg, all right? So what is the mass of mercury? Is 73.9, which is that percentage expressed as a mass now, right? Then what is the relative atomic mass of mercury from the periodic table? Is 201, okay? So the number of moles of mercury, it's 0.368 mole, okay? Where is that 0.368 coming from? How do we calculate the number of moles given the mass and the molar mass, right? So the mass from the percentage, right, it's 73.9. Divide by the relative, you take the relative atomic mass of that element as it is from the periodic table. It's unlike when you calculate the percentage composition, where you will be given the compound and you'll be able to see that, okay, when it comes to this compound, I'm having 2 nitrogen atoms, for example. Then I have to multiply the relative atomic mass by what? By 2. But in this case, you are trying to find the formula. We are trying to find the empirical what? Formula. So you don't know, the total number of atoms of mercury that are present there. You don't know the total number of atoms of chlorine that are present there. So hence, you need to take that relative atomic mass of that element as it is from what? From the periodic table. Okay, so we took that 201 as it is. We didn't say 201 times 2. So why should we say 201 times 2 while we are still trying to find what? The actual formula, or the empirical formula of that compound. So I hope it's making sense, right? So when you calculate the number of moles, the molar mass that you're going to use is the molar mass, the exact molar mass from what? From the periodic what? Table. You don't multiply it by any value, because you don't know how many mercury atoms are present, how many chlorine atoms are present. The only thing that is given there is the percentage of each element in that what? In that compound, right? So this is the number of moles of mercury, which is 0.368 mole. Then let's calculate the number of moles of chlorine, and mass over molar mass, okay? So these are number of moles, mass over what? Over molar mass. So what is the mass of chlorine? That percentage, 26.1, and then the mass, or the molar mass of chlorine, or the relative atomic mass of chlorine from the periodic table as it is 35.5. We can say 35.5 because we know chlorine is a diatomic molecule Yes, we know it is a diatomic molecule, but how many chlorine atoms are present in one molecule of this compound that we are trying to find, right? So we don't even know. So hence, we have to take that relative atomic mass of that element as it is from the periodic table. So what are we having as the number of moles of chlorine is 0.735 mole, right? So this is the number of moles of mercury, and then this is the number of moles of what? Of chlorine. Then from here, we have to find the ratio of mercury to what? To chlorine, right? So you divide the number of moles of each element by the smallest number of moles. So the smallest number of moles here between the number of moles of mercury and chlorine is the number of moles of mercury is 0.3, and then for chlorine is 0.7. So hence here for mercury, right? The number of moles of mercury is 0.368, and we are dividing by what? 0.368, because the number of moles of chlorine are the smallest, okay? Compared to the number of moles of what? Oh, sorry, the number of moles of mercury are the smallest compared to the number of moles of what? Of chlorine, right? So we have 0.368 divided by 0.368, then 0.735, that is the number of moles of chlorine, divide by the smallest number of moles, which is the number of moles of mercury, which is 0.368, right? So when you calculate here the ratio, 0.368 divided by 0.368, it should be what? 1, right? Let's check 0.735. 0.735, we're expecting 2 there. 735,368, 735, 0. Let's check if we are getting that 2 there. Okay, the calculator. So it's 0.7. Let me check again. 0.735 divided by what? 735, 368, ne? 368. Yeah, so it's 0.735, which is the number of moles of chlorine, divided by the number of moles of mercury, which is 0.368. So what are we getting here? It's 1.99, right? So 1.997 is approximately what? 2. That is approximately what? 2. Then, so hence here we're having what? 2. So the ratio of atoms of mercury to chlorine, it's 1:2. If it's 1:2, then the compound would be what? This one, which is Hg. How many mercury atoms are there in that compound? It's 1. How many chlorine atoms are there? It's what? Is 2. So it's HgCl2. HgCl2. So HgCl2 is the empirical formula of that compound, which contains 73.9% mercury and 26.1% what? Chlorine. All right. Then other examples, you have octane, right? So octane contains 84.2% carbon, 15.8% hydrogen by mass, right? So it contains how many elements there? 2. It's what is carbon and hydrogen. Then you are also given what here? The relative molecular mass of this compound, right? Which is what? 114. Okay? So we have 114. Then they want us to determine what? The molecular formula of what? Of octane, right? So how are we going to determine the molecular formula of octane, right? First thing that we need to do is to start with what? The empirical, okay? So empirical formula, you express those percentages as what? As masses, right? So what is the percentage of carbon is 84.2, right? It is 84.2, which means that the mass of carbon would be what? 84.2, right? What is the percentage of hydrogen? Is 15.8, which means that the mass of hydrogen will be what? 15.8, all right? Then from here, we have to calculate the number of moles of each element, right? So let's start with carbon. So it's carbon, number of moles is mass over what? Over molar mass, all right? What is the mass of carbon? 84.2. What is the relative atomic mass of carbon, or the molar mass of carbon from the periodic table? It's what? Is 12, right? So you take that relative atomic mass as it is, right? Because you are not given the chemical formula here, where you'll be able to tell that, okay, I'm having 4 carbon atoms, I'm having 10, hydrogen atoms, right? So hence you use that relative atomic mass of that element as it is from the periodic table, right? So it's 84.2 divided by 12, which is 7.0167 mole, right? And again, please be careful here. The issue of round-offing answers, ne? At least you must have 4 numbers after a comma there, or 4 digits after what? After a comma, right? So that you will get the accurate answer. Hence here you can see here it's 7.0167, right? So don't round off it to the nearest whole number, 1 decimal place, 2 decimal place, 3, at least 4 decimal places, then you'll get the correct answer at the end, right? Then let's calculate the number of moles of hydrogen. The number of moles of hydrogen, mass over molar mass, the mass from that percentage is 15.8. And then what is the molar mass, or the relative atomic mass of hydrogen from the periodic table? It's 1. So hence here we divide it by what? By 1. So we have expressed what percentages as masses. From there we have calculated the number of moles of each what? Element, right? Then from here we have to find the ratio of carbon to what? To hydrogen. How do you find the ratio? We divide by the smallest number of what? Of moles. So the smallest number of moles between 7.0167 and 15.8, the smallest is 7.0167, right? Then we are going to divide by that. So carbon, or the number of moles of carbon is the smallest, right? So hence we have check here, we've divided by 7.0167. So it's 7.0167 divided by 7.0167. Then that is our carbon, and then this is our what? Hydrogen. Okay? Then hydrogen, the number of moles that we got, it was 15.8, and then 15.8 divide that by the smallest number of moles. Then the ratio here is 1 is to what? Is to 2.25, all right? So the ratio there is 1 is to 2.25, right? Then we have to find what here? The empirical what? Formula, right? We have to find what? The empirical what? Formula. So how do we find the empirical what? Formula? We'll find the empirical formula what? Step number 4, this is the empirical formula. So the ratio is 1 is to what here? Is to 2.25, right? Which is equals to 4 is to what here? Is to 9. Where is that 4 is to 9 coming from? Okay? What you need to understand here, all right? If you look at, because they're looking for what here? For octane, ne? So actually here we are supposed to get what here? We have multiplied this by what? By 4, right? To get what? To get that 4, and then we have multiplied what? 2.25 by what? By 3. Okay. So 2.25 by what? By 3, which is what here is 4 is to what? Is to 9. So the empirical formula here is what? Is C4H what? H9. So but what is important here is the issue of getting what? The molecular what? The molecular formula. How do we get the molecular formula, right? The first thing that we need to do here is to calculate the mass, or the molar mass actually, of the empirical what? Of the empirical what? Formula. So how to calculate the molar mass of the empirical what? Of the empirical formula. The molar mass of the empirical formula the number of carbon atoms there is 4, right? So it's 4. So molar mass of C4 H what? H9. Okay? C4 H9. So it's 4 times 12 plus 9 times 1. All right? So 4 times 12 times 9 times 1. What are we having there is 57 grams per watt per mole. Then to get the molecular formula, is the molar mass of the molecular formula, which is 114, divide that by what? By the molar mass of the empirical what? Formula, right? So it's the molar mass of the molecular formula, divide that by the molar mass of the empirical what? Formula. So it's 114 divided by 57, which is equals to what there? Which is equals to 2. So then you multiply the empirical, which is C4 H9, by what? By 2, right? So 2 times 4 there, I'm having C8. 2 times 9 is what? Is 18. So C8 H what? H18. So that is what the molecular what? Formula of what? Of octane. So for you to be able to get the molecular, so you have to start with what? With the empirical. Then from the empirical, you can move to what? To the molecular. But how do you move from empirical to molecular? One, they will give you what? The molar mass of the molecular formula. Then what is it that you need to do? After getting the empirical formula, try to find the molar mass of that empirical formula. So then divide the molar mass of the molecular formula with the molar mass of the empirical formula, right? Then from there, you will have the molecular formula of that compound, right? Then let's look at this structured what? Questions. First question here. They want us to define the empirical what? Formula. Second question, we are given what? Vinegar, which is a dilute solution from what? From ethanoic what? Acid. And then we are given the percentage composition of each element present in ethanoic what? Acid. Carbon 39.9, hydrogen is 6.7, and oxygen is 53.4. Then for ethanoic acid, determine 1, the empirical what? Formula. Okay? Determine the empirical formula. 2, the molecular formula. If its relative molecular mass is 30, here it should be 60, right? So if its molecular mass is 60 grams per watt per mole, not 30, it should be 60, all right? So, but first question that they want us to do is to define the empirical what? Formula. So the empirical formula, it shows what? The simplest whole number ratio of atoms present in what? In a compound, right? It's a formula that shows the simplest whole number ratio of atoms present in what? In a compound, right? Then number 2, they want us to find what? The empirical formula of ethanoic acid and also the molecular formula of ethanoic acid, given the molecular mass of ethanoic what? Acid as 60 grams per watt per mole. So let's focus on number 2 now. Okay? So you have, let's check the percentages, right? So for carbon 39.9, 39.9% carbon, and then 6.7% hydrogen, and oxygen is 53.4. 53.4% oxygen. So these are the percentages, right? So first thing that we need to do, we need to express those percentages as what? As masses. So the mass of carbon will be 39.9 grams. That is the mass of what? Of carbon, right? The mass of hydrogen is going to be 6.7 grams. Okay? The mass of oxygen will be 53.4%. 53.4 what percent. Okay, that is the mass of each element. Mass of carbon 39.9, mass of hydrogen 6.7, mass of oxygen is 53.4. Right. So no. So here it should be 53.4 grams. So we are expressing those percentages as what? As masses, right? Then from here, we have to calculate the number of moles of each element. Let's start with carbon. Number of moles of carbon, mass over molar mass. The mass of carbon is 39.9. What is the molar mass of carbon from the periodic table? Is 12. Okay? Right? So you have 39.9 divided by 12. 39.9. 39.9 divided by 12. All right? So here I'm having 325. 3.325. Ne? 325. 325 mole. Right, so these are number of moles of what? Of carbon. 3.325 what? Mole. Now let's calculate the number of moles of hydrogen. It's mass over molar mass. The mass from the percentage, 6.7. Molar mass of hydrogen from the periodic table, it's 1. So here is what? Is 6.7 what? Mole. Okay? Number of moles of oxygen, mass over molar mass, right? The mass is 53.4. Molar mass from the periodic table, it's what? Is 16. What is 53.4 divided by 16? 53.4. 53.4 divided by 16, right? So I'm having what here? 3.3375. 3375. 3.3375 mole. Right, so these are number of moles, okay, of each element. The number of moles of carbon, 3.325 mole. The number of moles of hydrogen, 6.7 mole. The number of moles of oxygen is 3.3375 mole. Right. Then now we have to find the ratio of those of those atoms, right, or those elements. So the ratio, you have CHO here, right? So C. So it's CH is to O, right? Then the number of moles of carbon, right? It's what? It's 3.325. 3.325. And then for hydrogen is 6.7. And then here is 3.3375. Divide by the smallest number of moles. Let's divide by the smallest number of moles. So the smallest number of moles here, 3.325 and 3.3375. So 3.325 is the smallest, right? So the number of moles of carbon are the smallest here, because you check here is 3.325, but with this one is 3375. So divide by 3.325, the smallest number of moles, 3.325, right? Even here is 3.325. So here it will be 1. Let's check this one, 6.7. 6.7 divided by 3.325, right? So here it's 2.01, right? So 2.01 to the nearest whole number, right? To the nearest whole number is 2, ne? So here I'm having what? 2. Then here, what am I getting here? It's 3.3375 divided by 3.325, right? What am I having here? is approximately 1, right? 1.0073. So it's approximately what? 1. So here it's what? It's 1, right? So the ratio, then my empirical formula will be how many carbon atoms? 1, right? How many hydrogen atoms? 2. Oxygen atoms? 1. So this is the empirical formula of what? Of ethanoic what? Acid. CH2O. CH2O. Right. So this is the empirical formula. So now let's move from empirical formula to what? To molecular what? Formula, right? So empirical formula to molecular, right? So you are given what? The molecular formula of ethanoic acid. Ethanoic acid. It's what? It's 60 grams per mole, right? So if it's 60 grams per mole, let's calculate the molar mass of the empirical, which is CH2O, all right? So carbon is 12, oxygen, so the hydrogen is 2 times 1, which is going to be 2, plus oxygen, which is what? 16. So we have 16, so it's 12 plus 2, which is what? Which is 14. So 14 plus 16 is what here? Is 30. So here is 30 grams per what? Per mole, right? Then the molecular formula, right? It will be what? Molar mass of molecular, right? Molar mass of molecular formula divide by molar mass of the empirical. The molar mass of the empirical. Ne? So here, what is the molar mass of the molecular formula? It's 60. The molar mass of the empirical is what? We have calculated is what? Is 30. So what is 60 divided by 30 is what? Is 2. Right? So to get the molecular formula, so the molecular formula will be 2 multiplied by CH2O, which is going to be what? C2H4O2. And normally this is how we write it. CH3COOH. Right. So C2H4O2. Carbons 1, 2. And then hydrogens 3 plus 1, which is 4. Oxygens is what? Is 2. So that is the molecular formula of what? Of ethanoic what? Acid. So first thing that you need to do when you are dealing with finding or determining what the empirical and the molecular formula, express those percentages as masses if you are given the percentages. But it's not always the case that you'll be given the percentages. Sometimes they will give you the masses. So it's easier that way. You just go straight to calculating the number of what? Of moles. Then from number of moles, find the ratio of atoms, right? How do you find the ratio of atoms or elements? You divide each number of atoms or the number of moles of each element by what? By the smallest number of moles. And then from there, you'll get your empirical formula. How do you move from empirical to molecular? So from empirical, first thing that you need to do, calculate the molar mass of the empirical formula. Then they will give you what? The molar mass of the molecular. So you'll say molar mass of the molecular divided by the molar mass of the empirical. Then you'll get that value. Then you multiply the empirical formula by that value. For example, in this case, we got 2. Then we multiplied the empirical by what? By 2. Then we got that C2H4O2, which is the same as CH3COOH. That is ethanoic what? Acid. Right. Then let's check another question here, which is your question 3. Yes. Question 3, determine the empirical formula, right? You are given what? 56 grams of iron combined with 32 grams of what? Of sulfur to form iron what? Sulfide. Okay? So 56 grams of iron combined with 32 grams of sulfur to form iron what? Sulfide. So find or determine its empirical what formula. So you're given masses here. So if you're given the masses, just go straight to the number of what? Of moles. Okay? Go straight to the number of what? Of moles. So how do you get the number of what? Of moles? All right. So you have 56 grams of iron. Okay? And so it's 56 grams of iron and 32 grams of what? Of sulfur. Okay? So it's 56 grams of iron and 32 grams of what? Of sulfur, right? So they're looking for what? For iron what? The empirical formula. So empirical formula, it should be the number of moles of iron, right? Which is mass over what? Over molar mass, right? Then the number of moles of what? Of sulfur, which is mass over what again? Molar mass. So the mass of what? Of sulfur, right? So here it's what is this? The mass of sulfur is 32. Then the molar mass of sulfur, from the periodic table is also 32. So here the number of moles is what? It's 1. Okay? So first thing that you need to do is to, if you are given percentages, you express those percentages as what? As masses. But in this case, you are not given what? The percentages, but you are given what? The masses. So if you are given the masses, you just go straight to the number of moles. So the number of moles of sulfur, mass over molar mass, so it's 32 divided by 32, which is what? 1, right? For iron, what is the mass of iron? We are given 56, right? And then what is the molar mass of iron from the periodic table? It's also what? The 56. So even here it's what? It's 1. Okay? So you got the number of moles of each element. So from the masses, right? So fortunately we're given what? The masses. So from masses we can move to what? To number of moles, right? Then from here, after getting the number of moles, find the ratio of Fe to what? To sulfur, right? So the number of moles of Fe is 1. Even the number of moles this side is what? Is 1. So the smallest number of moles is 1. Even this side is what? Is 1. So the ratio here will be 1 is to what? Is to 1. So if the ratio is 1 is to 1, then the empirical formula will be what? Will be FeS. All right, which is iron 2 sulfide, right? Which is iron 2 what? Sulfide. So this is how you can determine the empirical formula and the molecular what? Formula. Then the last thing is the last question. So here we are just given what? The empirical, they want us to write down the empirical formula of butane. You are given the molecular formula of butane, which is C4H10. So you are given the molecular formula, which is C4H10. So the molecular formula is C4H10, right? Then from molecular formula to empirical, just divide by the highest common factor. The highest common factor between 4 and 10 is 2. So you divide this by 2, divide this by 2. Then the empirical, right? Empirical. Then the empirical formula, right, of butane will be C2H5. This is the molecular formula. Then the empirical, it shows the simplest ratio of atoms present in a compound, which is C2H5. Right. So our focus today, learners, it was just percentage composition and empirical formula, molecular formula. So determine the percentage composition, determine the empirical formula, and also determine what the molecular what formula. So that was our focus for today. So I think you gained something, and let's see next week. So next week our focus will be on water of crystallization, a limiting reactant also. Then from there we'll be looking at what the basic stoichiometric calculation. So I think for today we are done. Thank you so much.